Hello everyone. This is Dr. Amudha, Associate Professor, Department of Science and Humanities Physics, RMD Engineering College. In this video, I am going to discuss about the density of states and carrier concentration of matter. Density of states, Z of E, is defined as the number of available electron states per unit volume. So Z of E is equal to N of E by the volume of the metal. Z of E is equal to N of E by E cube, where A is the side of the metal. Now let us first find the number of energies levels in the cubical metal piece. For this, let us consider a three-dimensional space-bound sphere in the array of atoms in the metal by taking nx, ny, and z as a three-coordinate axis. Let O be the origin. So to find the number of energy states between the energy interval E and E plus D, it is enough to find out the number of energy states between the shell of radius n and n plus dn because it represents the energy E and E plus D respectively. Then, if you assume that per unit volume one energy state is present. So if you want to find out the number of energy states in the sphere of radius n, we have to find out the volume of the sphere of radius n. But when you take the entire volume of the sphere, it will have the nx, ny, nz to be both the positive and the negative values. But we know very well this nx, ny, nz is always positive. So we take only the octant of the volume of the sphere, which will give me nx, ny, nz to be a positive value. So first, the number of available energy states within the sphere of radius n is equal to 1 by 8 of the volume. So 1 by 8 into 4 by 3 pi n cube, that is equal to 1 by 6 pi n cube. Similarly, if you want to find out the number of energy states within the sphere of radius n plus dn, this is equal to 1 by 4 pi n plus dn the whole cube. But we wanted to find out the number of available energy states between the sphere of radius n and n plus dn, which is denoting the energy E and E plus d. So greater volume minus the least volume. So n of E dE, when you subtract and expand this formula of n plus dn the whole cube and simplify, we get back the expression as pi by 2 n squared dn. So I am going to write that n of E dE as pi by 2 n into n dn. Okay, we are going to substitute now the value for n. The energy of the electron in a cubical metal piece is given by E is equal to n square h squared by 8m square. When you find out what is n squared from this cross multiply and bring it to the other n, we get n squared is equal to 8m squared by x squared into E. Now find out what is n from this. You get back the expression like this. On differentiating the above equation, you get the value for n dn. Substituting this n and n dn in the equation, you get it as pi by 4, 8m a squared by h squared to the power of 3 by 2, e power 1 by 2 d. Since each energy level provides 2 electron states, then n of E dE will be equal to 2 times of this energy. 2 times into pi by 4, 8m a squared by h squared to the power of 3 by 2, e to the power of 1 by 2 d. On simplifying the above equation, we get taking this a cube outside, then you get n of E dE is equal to pi by 2, 8m by h squared to the power of 3 by 2 a cube e to the power of 1 by 2 d. Then when you divide by the volume of the metal a cube, you get the density of states. So Z of E dE is equal to pi by 2 8m by h squared to the power of 3 by 2 e power 1 by 2 d. So this is what is the density of states of a metal. By using this and the Fermi-Dirac function, we are able to find out the carrier concentration in the metal. So it is given by the formula number of electrons per unit volume in a energy interval n is equal to integral of Z of E into f of e. Substituting the value of z of e and substituting the value of f of e, and then when you simplify, okay, that is at the energy E is less than EF, we put f of e is equal to 1. When you simplify and integrate, you get the value for EF. EF is equal to 3n by pi to the power of 2 by 3 into h squared by 8. Next, we can find out the average energy of the electron at 0 Kelvin. So one more thing, n here you can get it as pi by 3 8m by h squared to the power of 3 by 2 ef to the power of 3 by 2. Now using all this, we can find out the average energy of the electron at 0 Kelvin. equal to total energy of all the electrons at 0 Kelvin divided by the total number of electrons. So we have to find out the total energy ET and also the number of electrons N. So number of electrons is given by integral of N of E into F of E. So substituting all these values, we get N to be pi by 3 atom by h square to the power of 3 by 2 A cube EF to the power of 3 by 2. Now we find out the total energy. Total energy is given by you have uh, this pi by 2 atom by h square to the power of 3 by 2 A cube root E dE F of E, and you know the value of F of E. F of E is going to be 1. So when you simplify, the only variable is this energy. When you do integration, you end up with this expression Et is equal to pi by 5 atom by square to the power of 3 by 2 A cube EF to the power of 5 by 2. Substitute this E total and the N value in the E average. What is E average? Is pi by 5 atom by square to the power of 3 by 2 A cube EF to the power of 5 by 2. Whereas N value is 5 by 3 atom by square to the power of 3 by 2 A cube EF to the power of 3 by 2. Simplifying this A cube getting cancelled, and all the terms whichever is common numerator and denominator getting cancelled. When you rearrange, you get E average is equal to 3 by 5 EF. Thank you for watching.